And it looks like we're live. Hello and welcome back. Today, diving into the Ethereum source code again. And where's my yellow paper? Ethereum yellow paper. PDF, Gavwood. So today, I wanted to look into receipts. And receipts are every transaction's counter side. So the blockchain is made up of a big list of blocks. Peers send transactions to the miners to go into a block, and when the miners have actually computed the transactions, and because the transactions in Ethereum are actually source code that gets executed, there's a receipt that goes with everyone, and the receipt contains logs that come out of the contract. It contains the results, but hopefully deep dive into it a little bit more. Ethereum go clear. Where is it? It's in the core again. Tmux cd core cd into types and receipt. So this is our file here, and it's quite short compared to the other ones. Only 200 lines. So let's start by pulling it up here somewhere. Transaction execution, contract creation, message call. Transaction receipt. In order to encode information about a transaction concerning which it may be useful to form a knowledge proof, zero knowledge proof, ZK snarks, or index and search, we encode a receipt of each transaction. We encode a receipt of each transaction containing certain information. Each receipt is denoted B block receipt I for the ith transaction placed in an index keyed tree, and the root recorded in the header as HE. So over here in the block, receipts root, hash of the tree. Transaction receipt is a tuple of 4 items, gas used in the block, the set of logs, and the bloom filter of them, and comprising the post, so it's got the state, the cumulative gas, the bloom filter, and a set of logs. LR trivially prepares a transaction receipt being transformed into an RLP serialized byte array. So they put it in a recursive link prefix again. So it's encoded a tree. Cool. So there's 4 items, and I'm assuming when we get to this receipt structure, we have 5. Post state status. Oh, status. That is the return status somewhere here it says too. If it's successful or not, or if it failed, because for some reason your transaction you submitted was retarded, they put a failed status and they take your gas that you've put in there. So they start off defining some blank byte arrays. Receipt status failed RLP, receipt status successful RLP. So there's an empty byte array if the status fails, or there's a 1 encoded in the byte array if it's successful. Constants. Receipt status failed is the status code of a transaction if it failed. No shit. Receipt status failed is 0. Receipt status successful 1. Okay, so they named the same thing twice. Here it's in integer. Here they've actually encoded it into RLP. This is super complicated because it's a 0 or a 1. So it's 1 encoded into hex, which is 0x01. Cool. Successful RLP is that. So that they're really just saving themselves some time by not having to send a uint, unsigned integer, to the encoder to get an RLP back, which is just going to be this. And I think a lot of programming, not counterintuitively, but if you want to write code for speed, sometimes doing things like loops and fancy encoding never really beats just a lookup table. Like, you can manually type, if there was like 30 of these, manually typing out all of these would probably prove to be more efficient than looping over 30 different things and incrementing each one. And it's funny like that, especially when you get to lower level stuff like C. So here we got the receipt. The results of the transaction are those 4 items that it was talking about in the yellow paper. And also, the post status. So the state, not sure what it is. It's just an empty byte array at this point. Post state. Is that going to say post state? What's it called? Transaction, post transaction state. Receipt down. Command C, F. The state is encoded into the tree structure. So I reckon this post state is literally what we were looking at yesterday. Where was it? Object state. I reckon it's one of these objects. That's based on nothing so far, but like it's one of these state objects, I reckon, encoded as RLP, is what comes back from the transaction. Which would make sense, because you have the miners execute everything, and then they specifically say what the state is in the receipt. And that receipt is what gets put into this tree. Unverified, stab in the dark at this point. But I don't reckon it's a state object. I reckon it's one of these ones. One of these lower ones. The account structure. I reckon it's one of them. Who knows? We'll see. Maybe. The function LR trivially prepares a receipt for being transformed into an RLP serialized byte array. So the yellow paper doesn't say shit about it. Cool. Cool. So first thing is the state of the account following the transaction. Possibly a state object account. Who knows? The status. At this point, all I can think is it's a 0 or a 1. If it's successful or failed. Transaction receipt. Each receipt donated for either placed in there. 4 items. State gas used immediately after. RU the set of logs. R1 the bloom filter. The log entries. No, where is... Can't find where it says receipt successful. So it doesn't actually refer to this in the yellow paper just there. It might be, I'll have to look in a bit deeper. So 0 if failed, 1 if successful. That's really all I can see it doing right now. Cumulative gas used. So after the transaction has been processed, it's going to have used some gas, which is the sum of all the transactions opcodes that are in the actual code to go in a contract. They all have a unique gas amount, which is stated somewhere here. Down the bottom, I imagine. External actor. Here we are. Cool. Fee schedule, which is 31 amounts corresponding to gas of the operations. So gas for 0 is 0. Nice. Gas for balance is 400. Gas for suicide is 200 refund amount. If you make a new account, transaction create. So that's how much gas each transaction uses. And you've written your bytecode. You've written your Solidity code, which has been compiled down to bytecode, which is a big list of sequential operations for the virtual machine. They all have a value. We sum those values up. That gives us the cumulative gas used at the end of the transaction. Plus, my understanding is there's a fee for the amount of storage on the chain as well. So if you use some form of storage, it's going to cost you some gas as well. Where did my receipts go? Transaction education is not after that. Receipt. We assert that RU is the cumulative gas used in a positive integer that the log's bloom R is a hash of. No. We assert that R is the cumulative gas used and that the logs RU is a positive integer, I guess. Cool, so that's a U int over here. Cumulative cost of operations and storage, positive integer, unsigned integer. Cool, good work. Bloom. Post-date status. So, before I get onto the bloom, I'll just go here and say logs. So you got a set of logs. The set of logs are 1. Let's see, conf 1. Nope. So you've got an array of the logs. This comes as a result of calling solidity logs. Logs are part of transaction receipts. They're generated by the clients, miners, when executing transactions and are stored alongside the blockchain. Logs are not part of the blockchain itself since they are not required for consensus. They are verified by the blockchain. So you got some logs. Events, yeah, cool. Events make logs. It's an abstraction of the login event watching protocol. You can have a series of up to 4 topics and some arbitrary length binary data. So this doesn't give me any sample code. A bit frustrating. Yeah, here it is. You know, your contract called test. You know, it makes it. And there's an event. 2 events that is defined. And then they've got a function which emits event A, but not B. Event 1. Event 1 gets emitted. So what comes out is that's the definition of the descriptor. So it's the ABI of the event, and not what comes out of it. Cool. So call one event, and that event creates a log, and that log gets saved here in this array. And you call the event as many times as you want, and do different things with it depending on what it is. I know CryptoKitties, for example, has an event for every sale that happens, or every purchase, or whatever you want to look at, or every trade. So there's a log, and that's how it keeps track of it. And that, I think, is theoretically also how they want the digital apps. So where you've got a web page that's got a Blockcoin backend to get information, it gets a log. So they send it a log, and the JavaScript watches the logs. When a log comes in, it's that. So you got your array of logs. This bloom is a bloom filter. And my understanding of bloom filters, which is very primitive at this point in time, is that it is a way to search through these things efficiently, but it brings up the possibility of giving false positives. So when they say here that, is it in here? You can have up to 4 topics. The way you so events are indexed or not indexed. Those which are indexed, which may number up to 3, are put inside the event signature to form the topics of the log entry. And then you can search by those events. And the way they do this in the blockchain is with this bloom filter. And my understanding of the bloom filter is that you've got buckets, and the different buckets represent different items. And if it's in 3 specific buckets, it references. So you got buckets here, bucket representing a binary. You got the 3 items here. The set X, Y, and Z. So there's a mapping between these. And if all of these items are true, therefore the item is contained in this byte array. So that's, it's a bad way of explaining it. I obviously don't understand it well enough on the list of things to understand it better. But you can search these logs efficiently, and especially when they're combined with all the other logs that have all happened for this transaction, for this contract over the life of its state. All the logs that have come through since it's been contract creation, you got to search through them. They are indexed somehow. There might be thousands and thousands of them. You can search through them using this structure. It allows false positives. That's probably the defining features. I'm going to have to dig into that at some point. I'm assuming this bloom is the file that's defined by Ethereum, and we'll dig into it then. Till then, I just accept it. That's an array. This allows you to search that array a bit better. Implementation fields, transaction at a hash, transaction hash. So this just links it to the actual transaction. So if you got a receipt, you can search for it. Contract address, same deal. If you got the receipt, you can search for it. If you got the gas used, I wonder how that's different to cumulative gas used. Cool. Cumulative gas used versus gas used receipt. Total amount of gas used when the transaction was executed. Gas used, cumulative gas used. Before the current one in the same block. Oh, interesting. Yes, there's a gas used. And there's a cumulative gas used. Gas price 20 Gwei. This doesn't actually show what he was complaining about, but gas used by transaction, cumulative gas used by the transaction plus the gas used in transactions executed before the current one in the same block. So the key is cumulative gas used in a block containing the transaction receipt. So that doesn't really actually say it there. Yeah. Receipts number, state receipts number 1 after each transaction. Resulting from applying the corresponding transaction to state resulting from a previous transaction. Yeah, so if you got contract having more than one transaction in a block, then you sum them all up as you go. So the first one's going to equal this gas used. There's a second one, it's going to be gas used between 2, and the second one will have a cumulative. That makes a bit of sense, I guess. One plague of the Bitcoin world is ASICs. Scumbags. Scumbags are making money off this stuff. Cool. So cumulative gas used, we'll re-edit that. Positive integer, sum of all contracts, transactions in block. And down here, which is not actually encoded into the tree, but is kept because Geth wants to have access to this information. It's very handy to have, I imagine. Gas used by single transaction referenced. So it's a contract, has a transaction, so you can find the contract here, you can find the transaction here. This is the exact amount of gas used by this transaction. If this contract has more than one transaction in the block, it gets summed together. And I guess because the transactions are listed sequentially in an array in the block, that the second transaction would be the sum of the first 2, the third would be the sum of the first 3, so on and so forth. Receipt marshalling. So now we go through the structures that are defined to save the receipts. So this here is probably exactly how it is saved in the tree, the receipts tree. So so they encode it with their special encoding. That's what gets saved. Here, receipt marshalling, I'm guessing this is just if they want it in hex for whatever reason. I guess printing it out, so you got to print out what goes into something. These are really just, they need 1,000 different structures to save it in the 1,000 different ways. One for like saving it in the database, one for saving it in the theoretical tree. The theoretical trees that they're making, and in the blockchain, and if you need to export it to be sent as a message, because you're transmitting these messages over a peer-to-peer network, they want them in a different way as well. So when you want to encode them in these special formats, they have a different structure, and there's a lot of overhead with just getting these receipts and encoding them into a format that can be used by the variety of different channels that these things are communicated on. So this new receipt, I guess as previously sort of keeps coming up, doesn't actually really do much. All it does is you pass it what the root, the cumulative gas used, and yeah, so you've already calculated what the state's going to be and done all your stuff with the transaction, and this is like the final step, is I'll just actually create the receipt. Failed is a boolean. If failed, it goes up and references the data structures they've defined here, and that's it. And it's an interesting if statement, because they literally just go, if this is true, put in the failed. If it is not true, put in successful. Which I always feel they've put it negative. They could have put successful. Is a transaction successful? Yes. If successful, put this one. But they did that way, whatever. Post state copy bytes. So making a new copy of the root, which I assume is their RLP encoding of this state object here. Again, I haven't seen exactly where it says that, but I just get the feeling that's what they've done. They're sort of chaining together. Cumulative gas used, you have to calculate that external. Encode RLP. Once again, they just define so if you've got the receipt, you can go encode RLP to a writer, which when you open a file file.writer, that's not how you do it, but when you open a file and go, you pass it to a writer, and that gives you options like writing to it. So you open up a file and you say you want to save it to this RLP encoding to it. Nothing too special there. Every single structure we've been through so far has an encode RLP and decode RLP, which is simply because that structure is Ethereum's way of storing everything. I'm pretty sure, yeah. The yellow paper goes into depth on it, and at some point we're going to go through that arbitrarily structured binary data. Cool. Set status. So there's a switch statement, post state or status equals receipt status successful equals post status fail if the length of the poster is equal to a nil common hash, an empty hash, post state equals post state or status. So you got a receipt, you've created a new receipt. And you can pass it either a 1, a 0, or an empty hash. And this function will set the receipt to be successful or failed, or if instead of passing a failed or a successful, this is a byte array. So we saw up the top here, they have the byte arrays here, and that's what they're comparing. Empty byte array or a byte array with a 1 in it. You can compare this to what's sent in. So a byte array, it's a byte array, so it can be whatever you want in there. It equals a 1, then they'll set it as successful. It equals a 0, they'll set it as failed. If it equals an empty hash, they'll put an empty hash in a post state. And I think that empty hash is probably useful because an account only has balance transfers, so you don't actually have to do too much to the state, so there won't be much going on. And if not, invalid receipt status error. Status encoding. It goes and digs up the byte array. No, it goes and digs up the integer from the structure here. So the status is an integer, and down here, if the integer is true, they'll give you the byte array of the failed or successful. It's kind of boring. They go to a lot of effort at the moment to put in the status if it's failed or successful in 1,000 different ways. Size, generic, returns approximately, memory used by all. And when it says approximate, they because they've got 1,000 different ways of storing these structures, either in a message that's sent over the peer-to-peer network, or saved as an RLP that's saved in a tree, or even just like a JSON that's just put into a weird file for you. They all have different sizes depending on what the overhead is for those transactions. So it estimates it by going through each item. You know, you got the post state, the log, and the data, and it's just summing up the size and returning that. And it's approximate because if you use a different one, it's going to be slightly different. It might be like a couple kilobytes off depending on the size of the item, so it's approximate. And down later on, there'll probably be an exact memory used for the RLP encoding. Receipts for storage is a wrapper around a receipt that flattens and passes the entire content of a receipt, as opposed to only the consensus fields originally. Yeah, okay, cool. So the consensus fields, what it's referencing is these fields that are in the yellow paper. So the yellow paper is just mathematically talking about, you know, if we want to prove that a transaction is on the blockchain, this is what we need to do. We create a receipt. We put that receipt in this tree, which isn't saved on the blockchain, but it's in this theoretical concept of the receipts tree. And that receipts tree is comprised of these 4 items, which is cumulative gas, bloom filter, and the array of logs. That's all nice and good. These are the consensus fields. But in the real world, we need the actual data. We can't just have like a theoretical reference to a hash of the last one. We need the actual data somewhere. So receipt for storage is a wrapper around the receipt that will flatten and pass the entire content of a receipt as opposed to only the consensus fields originally. So if we go back up to here, you can see there's these gas used, transaction hash, also the status. All this stuff isn't part of the consensus field. That's not going to get saved into the tree. We look at all these marshalling here. They're referring to these are the 4 that are actually the consensus encoding, receipt marshalling. See, this doesn't even have the list of the transactions in it. But this, it all sort of revolves around putting this into, receipt RLP status encoding. So if you go encode RLP, it'll only save the consensus fields. Receipt RLP. Status encoding, I didn't think that was in it. Cumulative gas logs log. Now here it is. The RLP doesn't actually have the post-transaction state. Or it does. LS. What's LS, do we reckon? Control F, V. The tree LS. Also LS, stop LS. Give me the actual definition. So hard to search. Tree LS. We define the block of rod as 5 ether. Hit a tree. If I go back to 1 and then search this. Individuals. Also LS. World state collapse function. Jesus. World state collapse function LS. And we get end of the world stuff instead of no, that doesn't actually even say it. So world state collapse function takes the state And as long as the state does not equal 0. What's P, you reckon? I think I'm digging into this too much right now. So, if I just have a stab in the dark of what I think a world state collapse function is it just takes a state and puts it into a smaller size for putting onto a blockchain or something. Maybe. So, when we're looking at these transactions, and they're getting logs as a result of it, the function LR trivially prepares a receipt. So this collapses the state into the tree. It's going to be the hash or something. Takes U, which is the cumulative gas, the logs, and the log bloom filter, and that's what is RLP serialized byte array, and thus the post transaction state is encoded into a tree structure. Yeah, so they don't actually save the state. The state gets saved on the block. Anyway, so when we're down here, where were we? Invalid read status. Size is a wrapper around a receipt that flattens and passes the entire content of a receipt. So receipt for storage. We're back to looking at items that make it convenient to save in memory rather than on a blockchain. So they actually take the status, the gas used, the bloom, the logs in an array of logs. Yeah, okay. So there's an array of the logs. Contract address, gas used. For all the logs, add the log to the array. RLP encode it. And flattens all the fields of the receipt. So we encode it, we decode it with DLP. And we're just continuing on as we've got this basic data structure here with the 4 items. Theoretically, they're good. We've got some extra items we need in there. But to save on the blockchain, it needs to be in a specific format. To send over as a message, it needs to be in a specific format. In all these different types, they need to be in different formats. So they literally define a heap of different structures, all saying the same thing, and they all just kind of talk to each other. And like, if I need to save it in this, you go, x dot save as something else, and you could do it that way. Or instead, what they do is you pass it in as a receipt for storage, for example. So you got a new receipt for storage, and then you'd pass original receipt. And then you'd have access to all these different that's really just encoding as RLP. Like that's the only function. So it's like .encode RLP, and that's the only thing you'll be able to do it for, because you've just been able to save it in a different format that's easier to read and has a better information for different contexts. Encoding, decoding. That's all the save for storage is. Receipts is just an array of the receipts. You can get the length of it, and this is really like the receipts.leng. It's the same as calling leng around the receipts, which is Go's length function. Get RLP returns the RLP encoding of one receipt from the list. So you got a list of receipts in an array, and you can dig it out. So that was super not that complicated. Really the only thing in it is this receipt structure, and they give a couple helper functions just to save it as an RLP, and just to save it as useful for storage. And all you're doing, and this is like the last step of making a block, is you've already calculated the transaction by going through it, executing all the bytecodes, looking at what it costs, and you've got all the information that's kind of resulted from analyzing that transaction. Then, once you've done all that, you take all this information, which is the state as a result of it, the gas used and stuff, and you create this new receipt. And then it gives you this structure, and it gives you 1,000 ways to save it, depending on how you want to, where you want to put it, which is either in the blockchain as consensus, or in a tree that's not actually saved on the blockchain, or if you want to send it as a message or save it in a database. So there's not actually that much to that one. And clear less. And what else is in here? Bloom 9. That might be a bit scary. Alright, so we got logs here. So obviously receipts are very closely tied to logs, because when you execute a transaction, the logs are the cheapest way to save information. If you save stuff on the blockchain, it's expensive and they charge gas. But if you emit an event, it's saved not on the blockchain, it's saved in one of these side trees. And it is equally useful because your server or whatever can analyze those instead of actually digging into the contract. And the contract doesn't have access to those logs later on, but most of the stuff you want to put, like, you want it to take off the blockchain and not actually put in. So these logs are kind of key, and the receipts are where these logs are stored. So if we get the receipt back up, so we've got an array of logs here in this receipt structure, and that is these guys here. And as usual, we've got, I wonder if I can find a log. Transaction execution, gas and payment, message call, virtual machine, execution environment, block finalization, uncle, reward application, mining proof of work, future direction, implementing contracts, conclusion, log, how to judgment through the transaction log. Logs bloom, comprised of the index of the log entry. So a log entry is a tuple of a logger's address, a series of 32-byte log topics, OT, and some number of bytes of data. So it's just got the address, an array of topics, and an arbitrary amount of data. So you got the address, you got an array of topics, which can be as many as you want, and then the data. The address is 20 bytes. $32 bytes, is it? No, 20 bytes there. So it is the address and T equals the total number of logs, I guess. 32 bytes. And you've also got the data, which is bytes. We define the Bloom filter function, M, to reduce our log entry into a hash. So they can just hash, which is, I don't know what that big V means. M3 248. So T was 248 is the amount of bytes. Yeah, okay, cool, whatever. It's just saying there's a log entry into a hash. It's a specialized Bloom filter that sets 3 bits out of 248 given an arbitrary byte series. Okay. So if you have a byte array that's length is 2048 bits, the Bloom filter can set 3 of those bits. And it can do so by taking the lower order 11 bits of each of the B is the bit reference function. Always digging up on Bloom filters, which is where my knowledge is weak at the moment. It's a bit embarrassing. Cool. So we got the address, we got the topics, and we got the data. They are the consensus fields. Here we go. This is terminology starting to come together now. Consensus fields. This is what is here. The address, the topics, and the arbitrary data. Address. An array of topics, which are just hashes. And the data supplied by the contract. Derived fields. Okay, cool. This is starting to make sense too. All this other stuff, which is not actually saved on the tree, the receipts tree to the side. The receipts tree has all the transactions in it, and in each transaction there is an array of logs, and each log has an array of topics and data. Derived fields. These are filled in by the node but not secured by consensus. This has a lot more comments on it than the other one. I don't even need to fill anything. Block number. Which block it's put in. Transaction hash. Which transaction this log was in. Transaction index. In the block, they list the transactions in a specific order, mostly determined by the miner. It's an array, and it's somewhat arbitrary. By seeing the sort options in the block transactions the other day, I would assume that it's mostly sorted by highest first is the people who give me the most gas, but also the same people are grouped together. So that's probably how the miners mostly set the order of the transactions. That's why they have to keep the index, once it's saved on the block, it doesn't change, but different miners might put them in different orders, and it's not determined mathematically or anything. Block hash. So you got the block number. So if we go ETH chain, and we got the top block, which is 6881743. That number is stored here. The hash is stored there too. Transactions, 186 transactions. This one looks like the top one. Why is it the top one? Because it has the lowest gas price. It's set only one gwei. Index of the log in the block. So each transaction receipt has one or more logs. Each block has one or more transactions. So if you cumulatively go through the first block and they got 5 logs in that, the first receipt of the block has 5 logs, be 1, 2, 3, 4, 5, and then continuing on, the second receipt has another 5, so it'll be 6, 7, 8, 9, 10, which I think that's what this would be. Index of the log in the block. Ooh. Removed field is true if it was reverted. So when they backed out some transactions, including the hacks to the DAO and stuff, those receipts that were deemed bad and had to be reversed probably made some logs, and you know, we've removed those logs as a result of our consensus, and we've set a field here, so when you go query them, and we'll probably do that at some point, because I mean that's probably the next step after understanding is we'll build some server that can like analyze transactions, and we'll go through and search for some logs. So you're querying the blockchain, getting some logs back. You get a big, long, nice table database of all the logs you can analyze, and they'll have this field which says removed if they're bad ones. Log marshalling, data, block number, transaction index. I don't know why they're marshalling it in this case, to save it to somewhere. I imagine it's like a print, so if you're searching stuff, you print it out. RLP log, address, topics, data. That's exactly what's going to go into the consensus. Storage log has all of it, so address, topics, data, and the block number, and the hash, and the index, and the block index, and the index. That's not saved in the tree, but it's saved in memory in the database, because this information is super useful. If you just have those things, yes, you can find where they lie because they're referenced in the tree, but the tree is kind of one directional. You start at the root and you go through it and go down. If you have a transaction receipt, sometimes you want to go backwards, which is probably when you're searching and querying. Encode RLP. RLP of a log, so specifically define a way to encode logs, which is address, topics, and data. Exactly what goes into consensus. Decode RLP does the opposite. Logs for storage saves it as flattens and passes the entire content including non-consensus fields. So same deal. They do the same thing here, but they save it for the memory. And this is, I think, is kind of recurring now. Is they've got for the block, for the transactions, for the logs, and for the receipts, is actually the structures aren't too complicated. And this defines 90% of what they are. And they'll have everything there, then they'll have a new log function that creates a new one. They also save it. They can save it. And the key is that they're saving it in a specifically defined way. I want to say protocol, but it's according to the white paper, it should be saved in a certain way for consensus. And then, outside of consensus, they want to save it a special way in the database, so when you search it, you get extra information. And I imagine Geth has, the people who wrote Geth had the choice of doing this, and it doesn't affect any other clients. So all the other clients like Parity and Ethereum, whatever, they all probably save this stuff as well, but they save it in different, and maybe they have some more stuff, maybe they don't. That might be interesting to look at, actually. Python, Ethereum, client, Trinity, Python client. Can I see the GitHub repo? And if we look here for log, utils, login, parser, logic, virtual machine, cool. Receipts, RLP receipts. They got the Bloom filters, they got their receipt class. Fields and receipt are a state root, gas used, Bloom's log. I want the log one. Can I? They're going to be a log. Yes. Logs. So they, in the Python equivalent, in the Python client, they have the log class. It's got the address, the topics, and the data. They are the consensus fields. That's what gets saved in RLP. So they're identical. And if they were different, what would happen is ETH. Give me core. ETH chains VM. If they were different, it means that Ethereum would fork, because these different clients would be trying to do different things. And I think the difference between Ethereum and Bitcoin was they made a lot of effort to define this yellow paper as the actual Ethereum protocol. And then we've got Go-Ethereum writing an implementation. We've also got Ethereum Pi EVM. Ethereum React, Solidity, Fiber, Soak, PyTest. Yeah, so we've got all these different clients implementing them differently. And when you've got stuff saved as RLP, that is the official yellow paper definition of what goes into either the tree or the blockchain. And this is specifically defined, and don't mess this up, otherwise clients that aren't the same as you will reject it. But this stuff here is your locally saved database, is stuff that's exported as reports. You know, you can do whatever you want here, and it's not going to fork the blockchain. If I put in another item here and said I also want, on top of the topics, I wanted the length of the topics, and then said that's an int. And then from now on, my version would save this. It wouldn't fuck up consensus, which is probably key. If consensus splits, then you get a fork, and then everyone loses. And I think that's what happened recently. November, Constantinople. Except for November release, is a, they define the protocol, they define what they want to do, and then all the clients race to build it. Parity, all of them do it, put in all these implementations. The implementations are discussed in the improvement proposals, and they go implement it. And in November, they tried to implement it, and this is the one that went wrong in October. And it failed. So now it's coming out January, because when they did try to implement it on the test network, the different clients forked. They proposed to activate it in November, but identified issues. Constantinople upgrade stalls. Features 0 transactions. Has been mined, but features 0 transactions. It's at a standstill. So it just failed. And as a result of the fail, they pushed it back to what's now going to be in January. So I guess that will conclude what I've looked at today. We've gone through transaction receipts. They start talking about logs and bloom filters. Holistic validity. Checking the serialization. What can we look at next? Block header validity. Probably something I need to look at a little bit. Gas and payment. Every transaction has an associated gas limit. This is the amount of gas which is implicitly purchased from the sender's account balance. So you set your gas price, you set your gas limit, and that's theoretically you're buying gas for your transactions. Like you're driving a car, you're filling up your car with gas, and there's this gas price. The difference is you get to set the gas price here, and they get to choose whether they accept it or not. And you say, this is my gas limit. And then your transaction goes, and any unused gas at the end is refunded at the same rate. It does not exist outside the code execution. Thus, for accounts with trusted code associated, so it just means it's within the transaction only. You don't store gas. You don't keep gas. You keep Ethereum. And every transaction you just set a gas price. Set to the beneficiary. So that might be a good one to look at, is the gas payment and transaction execution. So we did kind of look at briefly down the bottom here, there was appendix A, B, C, D, E, F, E, G. Here somewhere there is the list of the gas prices. So we might go through that tomorrow and dig through how much each transaction costs. Might set that much, and might briefly go into Solidity and try test some stuff. Anyway, thank you all.